Hi guys, Miss Green here to talk about radioactive decay and half-life. We're going to make this as simple as possible because it is a little bit complicated when we get into some of the questions. This chart is really helpful. It's going to help us to better understand half-life, the way it works, and how to use the math pieces that they may ask you on Regents questions. This chart is talking about the half-life of carbon-14, C14. So if we take a look at our reference table, we see that carbon-14 has a half-life of 5.7 times 10 to the third years. All that means is that it takes 5,700 years for half of the carbon-14 to break down. So over here, I see 5,700 years. That's the amount of time it's going to take for one half-life. So after no half-lives, well, that's right at that exact moment. That could be now. And so that's going to be 0 time. 0 half-lives, 0 time. But after one half-life, that means there's only half the amount of carbon-14 left, and now half of it has decayed into nitrogen-14. We know that it takes 5,700 years for one half-life to occur. So we're going to enter 5,700 years in our time column for one half-life to occur. Now, if there's half of the parent material, which is carbon-14, left, instead of 100%, which was the original, there's now 50%. We're breaking that in half. Sometimes they'll ask for the percent, and sometimes they'll ask for the fraction. We know the fraction of a whole is really just the same thing. It's going to be 1 over 1. Fraction of a half is easy. 1 over 2. Now, if we started at 100% of the carbon-14 only weighed 80 grams, and we only have half of the carbon-14 left, well, that 80 is getting divided by 2, so we have 40 grams left. Now, parent and decay. Parent is the original radioactive isotope. Decay is what it's changing into. So if we take a quick look back at the reference table, we see that the parent is carbon-14, the decay product is nitrogen-14. For the others, potassium is going to be our parent product. There's the element for potassium. And the decay product could be one of these two. Here's our parent. Here's our decay product. So nothing is ever vanishing or disappearing, it's just breaking down into a decay product. So for carbon-14, we know that that's the parent, our decay product is going to be nitrogen-14. So when we originally started and we had all 100% of the carbon-14, we didn't have any decay product. Nothing had decayed yet, so we had 0 grams of nitrogen, 0 decay product. When we had half of the carbon-14 left, that means that the other half has now decayed into nitrogen-14. Half and half makes a whole, so there's 40 grams of nitrogen left. 40 grams of parent, 40 grams of decay. These two numbers should always add up to our original amount of the parent product. 80 plus 0 is going to give us 80, that original number. 40 grams and 40 grams are going to give us 80, that original number. For a visual representation, I want to shade in this box in order to see how much of the parent, which I'm going to use in yellow, and the decay is left, so we can kind of visualize how much of each piece is left. So after no half-lives, we had the full amount of the parent product, the full 80 grams of carbon-14. So I'm going to shade this whole thing in yellow to indicate that it's the full amount, 80 grams of carbon-14. There's no decay product yet. After one half-life, that means that one half of the carbon-14 is left and the other half has become the decay product. So I'm going to shade in half of my box with yellow for the parent product and the other half with green to indicate that half of it now has decayed into nitrogen. For my second half-life, it took 5,700 years for one half-life to occur. I need to add another 5,700 years in order to get the time for my second half-life. That's going to give me 11,000 400 years for 2 half-lives to occur. All that was left of my parent material was 50%. Half of 50% is going to give me 25. Again, half-life, we're just cutting things in half. 25% is the same thing as 1/4, so 1/4. And if I had 40 grams of my carbon-14 and I cut that in half, then now I only have 20 grams of carbon-14. And again, these two numbers need to add up to 80. So if I have 20 grams of carbon-14, then I'm going to need to have 60 grams of my new decay product, the nitrogen, in order to add up to the 80 in total. This visual representation is going to look a little different. I still only have this half of the box of yellow in my first half-life. I'm only able to now have 1/2 of this half. So I'm only going to have 1/4 of my box filled in yellow, and the rest of the box is going to indicate that the rest has decayed. So if 1/4 is carbon, that means 3/4 is going to be nitrogen. Let's try some sample problems using the reference table. A sample of wood that originally contained 100 grams of carbon 14 now only contains 25 grams of carbon-14. Approximately how many years ago was this sample part of living tree? Well, I know that it takes carbon-14 5,700 years in order to go through 1 half-life. And I'm starting originally with 100. So originally means that there has been 0 half-lives, right? So I'm going to kind of set up a chart, and this is my advice for how to handle these problems in terms of grams versus half-lives. All right, so no half-lives have occurred. There's 100 grams of carbon. After 1 half-life, there's going to be 50 grams of carbon. But how long did that take? Well, the reference table told me that it took 5,700 years. So I'm going to add another part of my chart to indicate time. So I just took a second to make that a little neater, but after 1 half-life, I know that that took 5,700 years, and I have half of the amount, so if I originally had 100, I now have 50. Now, that's not 25 grams, so I'm still working. After a second half-life, again, I have to add 5,700 plus another 5,700. That gives me 11,400. And if I'm cutting that 50 in half again, I'm going to get 25 grams. Now that I have 25 grams, I've matched what my question is looking for, how many years, that's in my chart, so I go to 11,400, and I know that my answer is 3. I would really suggest to show some work off to the side, something like this, when you're answering these problems. Let's take a look at this one. This is a classic Regents question. We just have to read the chart. The graph represents the decay of radioactive material X into a stable decay product. What is the approximate half-life of the radioactive material X? So we need to pay attention to each line on my graph. I have stable decay product, but they're asking me about the radioactive material here. That's this dashed line. What is the half-life? Well, my half-life is going to be the amount of time it takes for half of the material to have decayed. So I'm looking at percent of material, 50 here. This 50% is going to tell me when my half-life is. So I'm going to go across and then travel down, and I get 5 years. But wait, all of my numbers are way larger. 5 times 10 to the third. We have to do a little bit of scientific notation. 5 times 10 to the third, I have 5. Times 10 to the third, meaning that I'm taking that 5 and moving the decimal point 1, 2, 3 to the left. That gives me 5,000 years. So my answer here is going to be 1. Okay, another question off the same chart. Which graph best represents the relative percentages of radioactive material X and its stable decay product after 15 15,000 years. So 15,000 years is my key here. Also, this is super important to know which is which. So my radioactive material, let's use yellow there, at 15,000, if I go over, is going to be less than 25%. So let's say half of 25% is 12.5% for my radioactive material. In terms of my stable decay product at 15,000 years, I'm going to go up and over. It's above 75%. To make sure that it adds up to 100, we'll call it 87.5%. So again, it's just about reading the key. I know that my white stable decay product needs to be the majority of my pie chart, so that's going to look like number 4. And the last one, each of these objects below has a different amount remaining of the original radioactive material X. Which object is most likely the oldest? So if we take a look at the radioactive material, we see that that is decreasing over time. So the one that's going to be the oldest is going to have the smallest amount of radioactive material left. So I just have to read. Coal has 10%, shell has 41, wood is 33, bone is 52. Based off the chart and what I know about radioactive decay, the coal must be the oldest because it has the smallest amount of the original parent radioactive material that remains. All right, guys, we will work with this in class. See you then.